maze, we'll be talking about navigating the maze with visual victims.
So, some of you may know, 2 days ago there was an earthquake in Southern California, and at a magnitude of 7.1, which is pretty ridiculous. But it's events like these where people get stranded in collapsed buildings, or in other cases the wilderness, or any other dangerous environment where they would need people rescuing. And usually we look towards our first responders who have to risk their lives in order to get these people out of these dangerous situations. What if there's an alternative? Robots. So robots hold a few advantages over our first responders. One, if we send robots over humans, we don't have to risk any human lives to save these victims. Robots can have more advanced sensors than just the 5 human senses, and they can be designed for any purpose that you want. And this is exactly what Robocup Jr wants to target with its maze competition. So the goal of maze is to, one, navigate the maze, and as you navigate the maze, there are victims, and you want to deploy rescue kits. And rescue kits are basically symbolic for food, water, or any other medical supplies that a victim might need to survive or get out. And victims are just heated pads or letters that represent victims that might be stranded. As you navigate the maze, there are obstacles, because in real life, you might have to get around like huge pipes or any debris that's fallen on the floor. And at the end, you have to return to the start so humans can retrieve you and use you again. So this is our robot, our development of robot that we use for the competition. So the navigation algorithm. So first off, in order to navigate the maze properly, you need to know where you are at all times. And to do this, we have 2 variables. The second variable, and that keeps track of where you are in the maze at all times. And we also have the orientation variable, which keeps track of which direction you're facing. And every time the robot moves, both of these variables get updated. So the map. If you want to navigate the maze properly and not revisit a tile like over and over again, you need to keep track of where you are in the maze. So our map is just a simple array of characters where each element is a tile. So let's say you have a maze that looks something like this. We could simplify it to look like a 3x8 grid that looks something like that. Then we can turn that into an array, so to the computer it'll look something like this. So that is what our map looks like to the computer. So if you actually want to use the map, you have to store information into the map so the robot can use it. So our map is made of a bunch of tiles, and each tile could have certain attributes about it. So what is the wall scenario in that tile? Have you visited the tile before? Does that tile lead to a ramp? And have you already dispensed the rescue kit in that particular tile? All of these are necessary in order to navigate the maze as efficiently as possible. So to actually store the map, we take advantage of how each character is stored inside the computer itself. So a character to the computer is 1 byte or 8 bits, and you can see an example of 8 bits up on the screen. And how we take advantage of that is each bit corresponds with a certain attribute about the tile. So, is there a wall to the north, to the east, southwest? Have you visited before? And does it lead to a ramp? And have we already dispensed a rescue kit for it? Yeah. So for actually traversing the maze, so our robot sets out in a simple traversal algorithm that is just very simple. So let's say we have a maze, and the circle in that picture is the robot, and we're facing north. So first it tries to go forward, and in this case it can. Then, if it can no longer go forward, then it'll try and turn and go to the right, in which case it can, and then it'll turn right again. It does this algorithm until we hit an actual dead end, and we classify a dead end as a spot where the robot can no longer move into a spot that it has not already been in. So then, once we hit a dead end, like in this case, then we have to look for a more complicated algorithm. So the algorithm we use is called breadth first search, and basically what it does is you can navigate through a tree of nodes, and it'll get you to the closest goal node that you want, and it'll get you the shortest path to that node. So what we did was, let's take this scenario back again. We would turn this scenario into a tree. Basically, each branch would be any tile that you can go to. So you would start at the starting node, and let's say you, as you can see, nodes 9 and 13 are possible nodes that you would want to go to. In the maze scenario, these would be any unvisited tiles that you want to reach. So as you can see, node 9 is much closer to the starting node than node 13, and our breadth first search would return the shortest path to node 9, which is the closest unvisited node. So to make things a little more interesting, the maze can actually have 2 floors. And the thing about this is our map has to be able to handle this, because the hardest part about dealing with this multiple floors is you have to make sure that when you start mapping the second floor, you don't override the first floor. So you can see we have a map up here that is similar to the one that I showed before, but this one is a little bit different. It's partitioned in such a way that the first floor and second floor will never overlap, so you won't ever overwrite any information. So you can see the blue tiles are specifically for the first floor, green tiles are specifically for the second floor, and the red tiles are specifically for connecting the first and second floor. Finally, we have to return to the start. And to return to the start, we look back at our breadth first search again. So as you can see, we are at our current node at the very top, and you want to get to the starting section. And as you can see, there's a few things that are different from our regular breadth first search. Firstly, you don't want to go to any unvisited nodes. You want to return to the starting section and the starting section only. And you have to ignore these unvisited nodes, because any tile that you haven't been in, you don't know the wall scenario. So that tile could be completely surrounded and you would have no idea. So you cannot consider these unvisited nodes during your breadth first search. Lastly, if you're on a separate floor when you want to return to the beginning, you have to go through a ramp. And thankfully, we can just look back at our map, as you saw on the last slide, who can tell you which tiles lead to a ramp and which tiles the ramp leads to. And using this map, you can get back to the beginning.
Yeah, so now I'll go over our letter detection algorithm. So just like a brief overview of the task, the goal is to detect the letters H, S, and U, which are going to be placed in front of generally a white wall from a raw image. So how the algorithm works is we first have the raw image, and then we must identify the letter, and we would crop the image accordingly, and then we would determine if the letter is either H, S, or U. And we're using C++ with the OpenCV library. So in terms of hardware, we're using 2 wave-share wide-angle Pi cams, one on either side of the robot. And we're also using the Stereo Pi with the Raspberry Pi compute module. So the Stereo Pi gives us access to 2 Pi cams. We actually did use a conventional Raspberry Pi before, but the issue here is that you can only attach 1 Pi cam. So instead we used 2 USB cams, but the USB cams had some disconnect issues, and also every time you powered on the Pi, sometimes they would switch ports, which could be kind of annoying to code around since you're unsure which is the left camera versus right camera. And we need wide angle Pi cams so that we can see the letters even when we're really close to the wall. So I'll go a bit more into the algorithm itself. So the first task is finding the potential regions of interest. So we first would threshold a grayscale image, and basically the grayscale image has pixels which have each a value between 0 and 255. So we're using basic thresholding. So basically pixels that are above the threshold are set to black, and then pixels that are below the threshold are set to white. So since we're using this type of thresholding, calibration is necessary depending on the lighting of the field. And also it may be helpful to use adaptive thresholding instead to compensate for shadows, which was an issue we had during the competition. After you threshold the image, then we need to find the regions of interest, and we're basically finding all the contours in the image, which are the outlines of the groups of white pixels on the screen. So here there's 3 contours. You have this little dot at the top, you have the letter, which is what we're interested in, and you have this curved contour, which is our tread. So we only want to focus on the letter itself. So we need a way to reject these 2 contours. And for error rejection, we have 3 main strategies. So first we would remove all the edge contours. Even if the edge contour turns out to be a letter, the letter would be partially cut off. and a partially cut off letter would, the algorithm would likely return a wrong result if the letter is partially cut off, so we don't really want to look at that. There's also an area requirement, so if the contour is either too large or too small, then we won't look at it because it's not a letter. And finally, we look at the height-width ratio of the letter. So the next step would be extracting the contours of interest. So we figured out that this contour is what we're interested in. How do we get to this cropped image? So the first step would be to rotate the image, which we do by basically finding the minimum area rectangle, and then finding the angle of that rectangle and rotating the image based on that. And then after the rotation, then we can basically crop out the image. And the key here is that right now the algorithm can only handle letters that are either face up or rotated 180 degrees, so upside down. So to avoid getting like sideways letters, we basically make sure that the height is greater than the width. Otherwise, we would rotate the image by another 90 degrees. Yeah, so now getting into like the actual letter detection, we came up with two different methods. The first of which is using what I'll call fill. So the concept is basically to slice the image into regions, and we want to calculate the percent of black pixels in each region. So if we want to figure out if the letter is an S or not, we can look at the leftmost and rightmost parts of the image. And you notice how with H's and U's, these parts of the image have a very high fill in terms of the percent of black pixels. So that's what we can use to determine whether the letter is an S or not. And then next, to determine whether the letter is an H or U, then we can look at this middle section of the image. And since the H has like a bridge, then the H would have a higher fill than a U or upside down U. So we actually didn't use this method for competition for two main reasons. First, it can be like problematic for warped images, especially since we're using a fisheye lens. So this H can actually end up having a very low percent of black pixels on the leftmost and rightmost regions if it ends up being warped. And also, this method requires a lot of calibration to determine the difference between U and H sometimes. So instead, we determine the letter using contours. So again, it's a very similar concept. We're gonna slice the image into regions and then look at each region. Except this time, instead of looking at the fill in each region, we're going to count the contours. So to determine if the letter is an S, we can split the image into its right and left parts. And note how an S has two contours on the left and two contours on the right, while H's and U's have one contour on both sides. And then finally, to determine if the letter is an H or U, then we can look at the middle 1/3 once again. And if the middle 1/3 of the image has one contour, then it must be an H, otherwise it's a U. So we did come up with a potential like combined method, which would also allow us to see sideways letters. So in this case, we would look at just the middle 1/4 region of all the letters. Middle 1/4 region cut both horizontally, so like this, and vertically cut like this. So if either has three contours, then it has to be an S. So here, if you look at this like middle 1/4 slither, you see there's three distinct contours. So that would clearly be an S. And then we can find an H to see if there's a sufficient fill in the middle 1/4 region. So for vertical H's, there would be a sufficient fill in the middle 1/4 region cut horizontally, since we would be seeing the bridge. So yeah, that's pretty much it. So thanks to our mentors, Dennis, Elizabeth, our parents for supporting us. Any questions?
Have you used any other cameras that you tested with, or?
Well, we used the USB cams we used before were like wide angle. We just got them off Amazon. They didn't work too well, so we switched to Pi cams instead.
So are you finding that that's the most effective?
Yeah, Pi cams are they're working a lot more reliably than the USB cams for us. So.
When you say more reliably, what kind of things were you running into with the USB cams?
The
Why were
USB
they bad?
cams, sometimes they would disconnect, and then also we had the two USB cams plugged into the Pi, and we also were communicating between the Pi and the Arduino. So there were three things all connected to the Pi through like serial USB, and basically every time we would boot up the Pi, the three different like ports would all switch around. So it was kind of hard to determine which corresponded to which camera.
So it wasn't the image quality, it was the...
Yeah, it wasn't the image quality. Yeah. Yeah, but the Pi cams are pretty good. Like the ones we're using work up to like 30 FPS or 40 FPS. Yeah.
All right, thanks for coming out.
Thank you.